Good evening, everyone. It's early evening here in Florida, and I have been fortunate enough to spend the day indoors. It's been a stormy day. In fact, we've had storms this week all up and down the eastern seaboard. And so, but I've had the fortune to spend the day inside and be able to make this video, get some things done. But in the last video, I talked about the observer effect and what happened when the data recorded from the randomly generated flashes of red and green light were later observed by human beings. What happened is that the humans were able to affect the data recorded on the floppy disks so that the flashes were no longer randomly generated. They were affected by the humans thinking about them. The effect this experiment has had was that it further fueled scientists who were increasingly of the belief that it isn't the act of measuring which determines a result. On the contrary, it's the act of observing, the observer effect, which collapses the wave function and brings about the result, which in turn brings about material world reality. Well, let's talk about material world reality. Most of us learned in school that atoms are the building blocks of the universe, of reality, and are made up of what are called electrons, which surround a nucleus. They orbit it. Quantum physics has now confirmed that even those electrons that make up solid matter can be thought of as waves. Waves of probability, meaning they may not even have happened yet. What they eventually end up doing may actually be based on whether they are being watched by a human being rather than a certainty that happens all on its own. Well, modern highly intelligent physicists, friends of mine, have said to me, yeah, but that's only the tiny. That doesn't apply to large bodies. Well, does that mean that what comprises the tiniest of the tiny in the universe isn't the same as the bigger version of itself? The issue is that quantum physics so far only gives sensible and accurate predictions of the tiny, so scientists really don't know how this applies to large things. Modern physics rests on two pillars, one on general relativity from Einstein, and two on quantum physics. The real problem is the two can't both be made to apply over all distances, so they can't both be right. Relativity works well for understanding the universe on the largest scale, like with stars and galaxies, but quantum physics, on the other hand, works well for understanding the universe on the smallest scale, like with atoms and subatomic particles. Scientists are still searching for the so-called theory of everything to cover both. And along those lines, some recent experiments have tried to demonstrate quantum effects in larger quantum objects, and their results may be pointing to there being no definite border between the two worlds. Well, the two worlds of physics, the quantum and the larger one of classical physics, are increasingly moving away from being thought of as two separate systems and toward being considered as one system. Even though it's usually not obvious, science is increasingly pointing to the larger physical world growing out of the tiny, with all of the weird behavior of quantum particles that we've talked about. Classical physicists like Newton and Galileo were studying the nature of energy in time, distance, and space. What they wanted was to devise laws that could highly and accurately predict what would happen in situations with which they had experience. But later on, when we had powerful enough equipment, nuclear physicists began to study particles at a much smaller level, the level of the atom. And after that, with even more powerful equipment, subatomic physicists became the quantum physicists. They're studying particles even smaller than an atom. At the other extreme, astrophysicists study really large bodies in space, like the Milky Way and clusters of stars within it, the movement and the gravitational field surrounding it, and how they affect the other stars around them. Astrophysicists and quantum physicists, to me, are both studying particles, but one just happens to be larger than the other. So let's go back to what's called the measurement problem, which we talked about in a prior video. So only when an object is measured, it seems, does it produce an outcome instead of waves of outcomes. The famed physicist Richard Feynman said the double-slit experiment, which we talked about last time, was impossible, absolutely impossible to explain in any classical way. Well, awareness of the critical role that measurement, or more simply the importance of the human being in the role of observation, may have in assembling physical reality can make you question what's really going on here. Insights like those of quantum scientists performing experiments are incredible. These insights may be even more correct than the material worldview of how the universe works, and to which most scientists today still cling. So this still begs the question, how is it that what we think we know is true, like solidity and our world around us, isn't what science is proving is actually true? While not satisfied with the human being as the explanation for the collapse of the wave function, sometimes scientists tried to measure or observe a particle and not include a human being in the process. So instead, they used a measuring apparatus that interacted with the particle in the place of a live human being. The theory was that the apparatus would cause the wave to collapse through that interaction, therefore proving that it was measurement and not observation. But all of this can be grouped into something called the decoherence effect, which is just a system in which quantum states interact with one another in the environment in such a way that it destroys the quantum state, it changes it. So what these scientists were studying was whether measuring a particle interacting could alter that quantum state. This measurement effect or observation effect are then just subsets of a more general term, the decoherence effect. They discovered that the use of a measuring device instead of a human observer doesn't solve the measurement problem. If we use one particle, meaning the particles that make up the measuring apparatus, to collapse another particle, then what was used to collapse the particle? Can you see? And so on and so on. So basically, we're missing the mechanism of how this occurs, in the words of the physicist Schlosshauer. This is due to the fact that science had already shown that particles normally exist as several mathematical possibilities rather than one actual object. This means there has to be something that is the source of the final collapse of every particle in the chain for our reality. We're then left with the observer effect, the human being doing the collapsing. The hidden meaning behind the observer effect, again, is another term for a human being. So on that pretty profound note, I'll wish you happy trails being in the now.